Let's look at the following problem. An undamped horizontal harmonic oscillator is shown below. Find the maximum amplitude of the oscillation of the system such that the upper mass, this one here, will not slip on the lower mass, that's that one. The spring constant K is given to be 10 Newton per meter. The coefficient of static friction between the masses is 0.5, so that is between the two surfaces right there. So given all the parameters, what is the maximum value for this x0? That is what we want to calculate. So as always, we shall start with a free body diagram. Let's do the free body diagram for this little m. Let's assume that at some point in time, the motion of this object is like that. So let's sketch a free body diagram for that little m. Since this is a simple harmonic motion, if the motion is leftward, that means the static friction that is preventing little m from slipping against the capital M, it's going that way. So that is the static friction. Of course, you have its weight, little m times gravity, and then you have this normal force, capital N. So that normal force is exerted by this capital M on little m, because little m is pressing on capital M, like that. And of course, you have the acceleration A. So from here, you see that immediately you can conclude that the net force is to the right, and that net force is quite simply the static friction. So in this case, the static friction equals little mass times the acceleration. Let's assume the static friction acting between the two surfaces is maximum. So maximum static friction, as we know, is given by the coefficient of static friction times the normal force. In this case, the normal force acting on little m is the same as its own weight, mg. Why are we insisting on maximum static friction? Because maximum static friction is indeed the static friction that must act on this little m so that little m doesn't slip on capital M while making the amplitude of oscillation maximum as well. So equating this to m times acceleration, you see m goes away, and we immediately get the acceleration to be coefficient of static friction times gravitational acceleration. So we have an important result from the free body diagram of this little mass. Now let's look at the free body diagram of this capital M. Because little m is attached to capital M, we must consider the free body diagram of this entire object as being a whole object. So let's label that composite object as little m plus capital M. If we look at the instant where the motion of this system is to the left, what are the forces acting on this composite object? Well, there is this spring force from the spring. We know the spring force opposes motion. That is a direct consequence from Hooke's law. Hooke's law states spring force equals minus k times displacement. So in this case, the direction of the force is that way. And then, of course, you have the weight, which is capital M plus little m times gravitational acceleration. And then there is this normal force that you can write as N with a subscript T going like that from the floor. And don't forget the acceleration of the system. It is the same acceleration as we have determined before. At the end of the oscillation, or where the displacement equals amplitude, the force F equals K, the spring constant, times that maximum amplitude. Let's call it XO max. That is using Hooke's law. But from Newton's second law, we know net force is provided by that spring force, and that is just capital M plus little m times the acceleration. So let's equate these two terms. K times maximum amplitude, which is what we want to find, equals capital M plus little m times acceleration. However, acceleration has been determined in terms of known quantities, so we can replace this a here with just that. And now we can solve for that maximum amplitude. And it is quite simply the sum of the two masses times the coefficient of static friction times gravitational acceleration over the spring constant. Let's substitute the figures. Capital M is 200 grams, little m is 50 grams. Together they're 250 grams, so that is 0.25 kg. Coefficient of static friction is 0.5, so times 0.5. G is 9.81 meter per second squared, and spring constant is given to be 10. That will give you an answer of 0.123 meter, or quite simply 12.3 cm. And that solves the problem. Thank you for watching.